Thank you for inviting me. When I was thinking about what do I want to say today, I thought, I can tell you about one of my latest research projects, and you'll be all excited at the moment, but a couple of years from now, the field has moved on, it might seem a little stale. So instead, I thought, let me try and distill over 30 years of experience developing and optimizing and characterizing storage systems into, well, 1 hour or so, maybe. Necessarily, I'm going to be leaving a lot of stuff out, but I'm happy to talk to you. All right, so let me start with this statement, okay? Storage is complex. Data is everywhere. Life is good. All right? So let's see if this holds up by the end. All right, let's start with some motivation, okay? We've all seen this storage hierarchy pyramid, right? Where at the bottom we have bigger, slower, cheaper devices. At the top we have smaller, faster, more expensive devices. All kinds of devices have come through the years and they kind of move up and down, some overlaps. But the interesting part is there's orders of magnitude performance difference between each of these layers and across them. There's not that many fields you can think about where the slowest and fastest operations differ by 6 to 8 orders of magnitude. That poses a challenge for us, a significant challenge. And I've been thinking about this for a long time, trying to think, why is it that this has kind of remained true over time? Yes, over time, everything gets cheaper, faster, bigger, but these differences remain still true. And I think it boils down to economics and physics. If you want to move some mechanical device faster, it's going to cost you more energy. More energy costs more money. If you want to move electrons from here to there faster, it costs more energy, therefore it costs more money. And fundamentally, that's a limited resource. And so we can't afford to create storage systems that are going to put all of our data in some non-volatile, super fast device. It just would be prohibitively expensive. So fundamentally, we're always going to have these kind of tiers, and we're going to have to deal with them no matter what. Okay, now, the storage stack is deep, and it's getting deeper. And as I said, data is everywhere. So I'm going to use this simple example here. I have some file system X. I have some benchmark running in userland. It goes to the block layer into some storage device. And I'm going to use this running example in my talk of, I took some file system. I wanted to add some features to it. Let's say I added encryption to it. Why? Because that's my favorite example. Okay, so I have now a vanilla file system and one that I modified to add some encryption to it. But there's a lot of things I might want to do in this system. For example, there's a trend to move more and more stuff into userland. So now I have to worry about the userland components in the system, not just what's in the kernel. There's memory and caches at every layer, and they interact in very complicated ways with every layer of the software. What about networking? Maybe my storage goes to a local area network like NFS or a wide area, far away network like cloud. I have to figure out that complexity on top of everything. There may be multiple storage devices all the time. The different storage devices, different characteristics, they come up. What about other layers of virtualization like LVM, RAID, more virtualization? There's a lot of this kind of stuff that happens. And so my simple file system that I want to characterize now looks a lot more complicated because there's a lot of components I have to worry about. Fundamentally, what we have to worry is how can we isolate the impact of different components on our performance? And hopefully I'll show you some of these examples. All right. Now, storage benchmarking is time consuming. And I want to give you an example of what I think we have to do. So in my opinion, a typical process of doing some research project, and by the way, this applies to industry as well, is we do a little bit of literature review, a good amount of design, a good amount of implementation, and some testing and some benchmarking, and we're done. We call it a done deal. In reality, the picture looks different and definitely should look different. The reality should look more like this. First of all, we should do more literature review to find out everything that's available in the state of the art. The design implementation to be relatively small. We should spend a lot more time on testing and debugging and a whole lot more time on benchmarking such a storage system. And there's reasons for that because benchmarking often reveals problems. It reveals bugs and crashes. Your system crashes. You have to go figure out what the bug is, fix it. It may reveal a performance bottleneck. Something didn't work the way you expected it to work. You're gonna have to go and figure out where's the problem and fix it. Maybe an implementation problem, maybe even the worst case design problem. You have to go back to the drawing board, redo everything. All these things consume more time in benchmarking as you go back to implementation, go back to even the design. That's why it takes a lot of time. Moreover, if you change your code in any fundamental way, you have to throw away all the results that you did before. You have to start them from scratch. And that's not even taking into account any kind of hardening of the code for any kind of release, any regressions you might want to run or release, any code or data releases. All right, and when you see this little Mr. Burns icon, that means I have a dirty little secret to tell you. In fact, I have two of them here. The first thing is literature review is very critical. If you miss some important related work, that's usually a good way to get a paper rejected. I tell my students that they better find out all the papers that are relevant and cite them, especially those of the program committee members, because you don't want to offend them personally. All right? The other thing that I want to tell you is, how do I review papers? Before I review papers from beginning to end, I usually look at the abstract, a little bit the intro, and then I jump to the evaluation. I want to look at the figures. I want to look how good they look, how well explained. Are they self-explanatory? Do they look clean? Are they impressive? If I see what looks like good evaluation, I'm already thinking very positively about the paper. Because you can have the greatest design, but if you have not evaluated properly, then it's hard to believe that what you have is really working very well. So that's a good, additional good reason why you want to pay a lot of attention on evaluation. Okay, so let's talk about what it takes to do benchmarking, all right? So what tools should you use to benchmark? There are lots of tools, but there's really more classes of tools that I want to tell you about. Well, one example is micro benchmarks, like FIO and DD. There's many more. I couldn't even list all of them, so I don't want to tell you use this tool or use that tool, but rather think about classes of tools. So what do micro benchmarks are good for? Usually they're good for testing specific features or narrow features, isolating the worst case performance of a particular feature. But the criticism is that they're not that realistic because they are very specific to one particular feature that you're testing. So there's what's called macro benchmarks, bigger things that they try to test multiple operations. They're considered more realistic, but still they're sort of synthetically generated, and many of us will say, well, maybe that's not as realistic as possible. So, of course, now there's traces. I can use some traces, and thankfully SNIA has lots and lots of these traces that are being collected and released. They're considered more realistic because usually they're captured under real scenarios, but traces can still be stale if they're very old, and what system they were captured on. And it's a good question of how do you replay them. If you replay them in clock time, it could take as long as the original trace was running, or do you play it as fast as possible? Those are all kind of questions. So the question is, which one of these options you should choose? And the right answer is D, all of the above. You should really pick as many of those and have a wide spread so that no one could have a question like, oh, I don't know how your system will operate on this mode or that mode. Okay? Now, let's see how many of these benchmark experiments you have. So let's say I've selected 3 kinds of benchmarks, 1 micro, 1 macro, and 1 trace. Let's say in terms of workloads, I selected 1 sequential, 1 random, and 1 mix, so I can have kind of good coverage of all kinds of workloads. And now what about the workload size or the cache size or some other parameter? Well, I want maybe some default and then maybe something a little larger, something a little smaller. Because again, if you pick only one thing, it's very hard to know what impact that parameter will have on your overall performance. Number of threads or something similar to that, maybe I'll pick 3 different values. Remember this was an experiment where I have an encrypting file system that I developed. So of course I have to test the CPU bound operations like hashing and ciphers, so maybe 5 more parameters. How many times should I run each experiment? At least 5, so I can get some good statistical stability. All this alone will get you over 4,000 experiments. At 1 minute per experiment, that's over 2 days of clock time. If you go to 2 minutes, it's 5+ days. If you go to 15 minutes, it's 42 days. And these are highly conservative values. because a lot of experiments actually need to run much longer than that. We run experiments that each run will take an hour or two. So now you can see how experiments could take months to conclude in order to get really good, stable results. That's why benchmarking can be so time-consuming. All right, now let's talk about presenting data. All right, I have not seen any information about how to present information, and not just in talks like this or talks like many of you are giving, but presenting it in print media. The last time I've seen something like this was when I was in grad school, so I'm hoping that this will serve as sort of a resource for many of you to use. All right, so let's take this particular fictitious example. I have two systems, the baseline system and my system, and I ran it under 3 different benchmarks. It could be the same benchmarks with 3 different configurations, but I have 3 different settings, and I calculated some metric, and I presented it. And I put it into these bar graphs, all right? So the question for you now is, how many wrong things do you see with this figure? All right, let's start. Y-axis starts at 0. Many tools do that by default. It's very annoying, frustrating, because it magnifies the impact of what you're doing. For example, on the leftmost graph, it seems like my system is about 3 times better than the baseline, but in reality, it's not. So I would urge you to make sure that you start your y-axis at 0. If you absolutely have to start it not at 0, make sure you put a big bold letter saying this is not starting at 0, and then there should be a good reason. The y-axis label is missing. What is it? I don't even know what is it that I'm presenting here. So you have to provide this information. Students tend to do that when they just kind of try to get you quick and dirty results for next week's meeting. And I urge them to be as professional and thorough as possible on this. There's too many labels here, just too many numbers to see. I don't need that many numbers. There's also wasted space here. The legend can be moved where this white space is. And if you do that, you probably save a couple of lines of text. How many of you have wished you had more room to write in the paper? This is one example. Don't waste white spaces in your figures. There's also no numbers on top of the bars, no measure of stability like error bars. So lots of little things that are wrong here. Well, let's go fix all of them. All right, so I fixed the y-axis at 0. I added a label. I reduced the number of labels. I moved the legend over. I put numbers on top of the bars and error bars. There's still several wrong things here. All right, first thing is, there's a typo. Have you noticed it? A little typo. Seeing typo in a figure, indicates, maybe this person wasn't as careful in their benchmarking. It's also more time-consuming to fix. You can't just go to the overlift and fix it. You have to go to the source of your figure, fix it there, regenerate the figure, regenerate the embedded object, move it over to overleaf, rebuild your paper. So little things like that do matter for how good a presentation looks like. There's also missing units. I don't know what the unit is, all right? It's still too many zeros for my eye to see. Perceptually, we don't want to see that many numbers. Too many digits of significance. A lot of people just do it average, and then they give you like 6, 7, 8 digits of significance. Do you really have that much statistical stability that you need that many digits of significance? Probably not. Okay, and here's something that the presentation leads to. Presentation is not just making things pretty, it leads to analysis and analytics in evaluating, because the first thing you should see here is, something is going on. Why are these error bars kind of high? What does it mean about the stability of my results? Maybe something is going on I should investigate. All right, so let's go and fix these, all right? So I fixed a typo in the y-axis label. I added proper units. I put commas around the 0 so it's easier for me to read. I rounded up some of the numbers, but I still think that the y-axis labels are a little harder to read. The scale is a little too small, bytes per second, and we're talking about thousands of those. Maybe we can fix that. So let's fix that, all right? So I rescaled everything to kilobytes per second because it's so much easier to understand it. Smaller numbers are easier for us to understand. I rounded up the numbers on top of the bars. So now it looks a lot easier to understand perceptually. But here's a good question. Do I really care about what are the absolute numbers on top of the bars? Or do I really care about the differences between them? Like how much better or worse my system is doing compared to the baseline system. So now I'd like to give you one of my favorite quotes attributed to Isaac Asimov. The most exciting phrase to hear in science, the one that heralds new discoveries, is not "Eureka, I found it," but rather, that's funny, something is going on here. All right? So coming back to the figure, what I will do instead is change it. So instead of giving you the numbers, I'm giving you the magnitude differences, which is probably what is most important when you want to convey as much information in as much space and as quickly as possible. So here I'm simply showing you that my system does 37% better on benchmark A and 18% better on benchmark B. If I really want the absolute numbers, I can kind of look at the y-axis. But you can see that it's doing 19% worse on benchmark C. So that's funny. What is going on here? Why are the trends reversed? I was doing well on 2 benchmarks. What's going on? This is something that needs to be investigated. Okay? Now, do you see these 2 error bars and how they're large? In fact, they're overlapping. Okay? From a statistical perspective, when you have 2 confidence intervals that overlap themselves, it means that the true mean can be anywhere in that confidence interval within some probability. That means that the actual mean of these 2 numbers for benchmark C can be anywhere in there, and in fact, maybe the trends are reversed. Maybe it's not 19% worse, but some number better. This is something that needs to be investigated. You have to figure out, why am I getting this? Are my results not stable enough? Do I need more run? Do I need to investigate what is going on? Okay? Presentation scales. Suppose I have something like that where I have small numbers and very large numbers. You see it all the time. And there's also a lot of white space, and it's very hard to really see the differences between them. Something very simple that you should always try to do is just use a log scale. Log base 2, log base 10, log base whatever. Now it's much easier to see the numbers. But log scales are harder for people to perceive because we don't think in exponential terms. So if you use log scales, make sure you say it's log scale, put in a caption, and highlight it in the text of your paper so people would know that you're using log scale. So it's very, very clear. But this is an example where you should always try log or not on linear and see what works better, what looks better. Easier to compare. All right, let's go to a couple other examples. Here I want to tell you about these kind of directionality trends and crossovers. I have an experiment where I have like 3 systems, and you see that the y-axis is in throughput, the x-axis is logarithmic, it's workload size or some other parameter that grows exponentially, and I have 3 systems where I measured the results. And when you look at it, looks nice, but there's a lot of things that need to be investigated. To start with, the first system kind of grows linearly very slowly, and yet the x-axis grows exponentially. And this is kind of a good question. Why is it that if I'm growing this metric of workload size exponentially, why is the throughput only growing linearly? That just something kind of like doesn't make sense. It needs to be investigated. The second system, the trend goes down. Why is this one getting worse when the workload size grows? This needs to be investigated. Why are the trends reversed? The third system goes up and then goes down. What happens at that peak that makes it sort of an optimal point, and what happens after that it starts to get worse? This kind of behavior needs to be explained. Also, what is this dip here? What's going on there? Is it an anomaly, a wrong data, something went wrong, a true behavior? All these things need to be investigated. The other things that need to be investigated is, in my opinion, every time you see 2 trend lines cross each other, okay, the crossover is an interesting inflection point where something happened where one system overtakes the other for some reason or another over a metric. All these things need to be investigated. And so, simple figure, there's 6 things you have to investigate. You can see how long that could take to explain, analyze, and then thoroughly document what is going on. Now, this is a throughput graph. Very often we put throughput next to latency. I have seen it even this week, all right? Throughput and latency usually go hand in hand. The problem is that their directionality is opposite. For throughput, higher is better. For latency, lower is better. And when you see it without actually paying too much attention, it takes extra mental thinking to really see the difference and understand, oh, okay, that's what's really better, that's what's really worse. If it takes longer to understand a figure, it takes longer to understand a paper, it detracts from the quality and the presentation of the material. There's a very simple solution to this. Smile. Just put these smileys on or some other metric that tells you what is better, higher or lower. I've started this 20 years ago, these little smileys, and I was hoping that more people will do that. So I hereby give everyone a royalty-free license in perpetuity to use these smileys anytime you want. You don't have to credit me at all. Just please do something like that. All right. But there's another good question. Do we even need bar graphs? Bar graph is just a big rectangle of a fixed color. Maybe instead of using bar graphs, just use box plots. Box plots give you a lot of information in the same space. And they're usually more suitable for storage benchmarks because we have all these orders of magnitude differences in behavior. They give you quartiles or you can design them to do like a 10% or 1% regions, a median, means. They even will show you any outliers that you might have. And so those are much more useful than just defaulting to bar plots by default. They give you a lot more information in the same space. Outliers. You shouldn't really have any outliers in systems research. If you do, you have to figure out what's going on. Now, what will be a true outlier? Here's an example. Suppose I configured my server, I'm running my experiment, I have like 10 experiments to run. Each one is going to take 1 hour, and I'm just repeating the same thing, and I'm launching it on my system. Unbeknownst to you, another user logged into the system and started to compile things. So obviously they're going to mess up your timing in the middle of this run. The memory, the I/O, everything's going to go off. That's an outlier, okay? And in theory, you're supposed to throw away those results because they're not representative. But a much better way to handle it is to avoid these outliers in the first place. It is control the environment. Make sure you don't have any jobs that can wake up in the middle, like cron jobs or periodic things that just kick off and do things that could screw up the experiments. That's much better than having to report outliers or even eliminate them. Next thing I want to tell you about is choosing colors. Okay, this is something I've learned by collaborating with visual analytics people. The two URLs you see on the bottom right are from two popular websites that are used by visual analytics people whenever they have to use more than 3 or 4 different colors to present things. It's important that you use the right colors that will look good and sufficiently distinguished in whatever media. You can choose the number of colors, you can choose whether you want to optimize for color, black and white, grayscale, the depth, whether you want it for print or display. You even can optimize for color blindness. One of the things that many people don't know is that everyone perceives colors slightly different, and everyone has some measure of color blindness. In fact, what I perceive as green and blue might be different than what you are perceiving as green and blue. And so choosing the right colors is important if you want something to look good. I've seen some presentations this week where there was a lot of shades of the same color, and I have to squint a little harder to see which one is your system and which one is other people's system. So these are good tools to use for presenting materials. Let's go to analysis. All right. Going back to my figure. Remember the figure of my encrypting system, and then I have all these components that are interacting, and I have to analyze things. Well, the first thing I probably have to do is measure the behavior of different components. I have to start by measuring what is my throughput of my storage device. What's the maximum that they can handle? Because my file system won't be able to do much better than what the underlying hardware can do. So I have to measure that to begin with. How's my network doing? It's very easy for modern processors to overwhelm in 1 gig network and even 10 gig networks. And so are you bottlenecking on the network, or there's something going on in your system that you've developed? All these things need to be measured. How is your CPU doing? How well does it handle all these CPU-bound operations? You need to measure those individual ones. What about the memory? How fast is your memory accessing data in and out of memory? What about the user-level components, context switches, data copies? All these things, you have to know them because they become bottlenecks in understanding and analyzing your system. So those are the first kind of baseline numbers you need to get, so you can, it will help you to explain the results eventually. All right, but now you want to analyze the behavior of your own system. You have some software system, you want to find out where are the bottlenecks in my own code. You want to kind of dive deeper and maybe find bottlenecks and optimize them. So the question is, how do we isolate the impact of specific functions or components deep inside your code? There's lots of techniques. We can use eBPF, trace points, block trace, all kind of tracing technologies, and they generate tons and tons of data. That's wonderful. The concern is that they might, first of all, there's going to be a lot of data that they generate. There's a lot of overhead. They might actually interfere with the behavior of the system because they add too much internal overhead. And depending on how those systems are designed, they may actually lose events. Systems like trace points use a ring buffer, a lockless ring buffer, and then you have to pull the data out of it to user land as quickly as possible. If not, you actually lose events. And so you may not get all the events. But the question is, do you really need all those events? Maybe all you need is just to capture averages, some number inside your particular function. So you could add some code that will measure and then average the number, let's say latency of your functions inside your code. But maybe that doesn't give you enough information. You want more than an average, but you don't want to have all the overhead of tracing. Is there something that you can do to capture more information efficiently? And there is a technique that we have developed more than 20 years ago. And the idea is this. Step one, you sample the timestamp counter. Every CPU has some sort of a tick counter. You sample it. Then you run your function, whatever function it is, you can wrap it. Then you sample in step three, the timestamp counter again. You subtract them, and then essentially you do shifting of this number to the right. Shifting to the right is essentially dividing by 2, and then you calculate a bucket number, and then you stick it in some vector array or integer array called a histogram. Essentially what you create is a small array of integers that represents a histogram of the latency in powers of 2 of your system. And you can sample this vector either at the end of your experiment or periodically to get periodic results. So this technique has negligible memory overhead, and the CPU overhead way back 20 years ago was about 4%, and it was mainly attributed to the number of clock cycles that are needed to sample this TSC register. Nowadays, they're even faster. All right, so let me show you an example of what you can get out of something like that. All right, here's an example where we instrumented inside the kernel and we measured, we essentially collected these histograms of different file system operations. This happened to be an experiment. We were doing a recursive grep over some source tree, and this happens to be the read operation, but we did it for every possible operation. You can see that the y-axis is the count in log base 10. The x-axis is the bucket in terms of log base 2 of the clock ticks. And I've used something interesting here. I've used an x2 axis by calculating for that particular CPU, what would be the average latency of that bucket? So now I can give you kind of both ways of presenting the information. This allowed us to see the complexity of this particular workload. It's not a nice normal distribution. It's actually multimodal here. So with this, we were able to analyze what was going on, and this is what we found out. This last mode, the slowest one, that's when the disk had to move, disk head delays. The next one is when you hit the disk cache. You still have to do I/O to the disk, but you grab something out of the cache. The next one, as you might guess, that's when we hit the operating system cache in memory. So it's obviously faster, moving to the left. And what's that one all the way to the left that's at like a nanosecond? How is I/O operations operating at that speed? That's more CPU speed. It turns out that was an optimization in Linux that if you try to read past the EOF, it doesn't even go to the page cache, it just returns 0 right away. So all these things were very important to understand. And the dirty little secret here is that depending where your workload falls into these buckets, you're going to have orders of magnitude different performance, from very fast to very slow, depending on how your benchmark distributes the number of operations to different elements. But this allows you to explore and explain what is going on inside your system. Here's the next example is when I sample these histograms every second. So in this experiment, again, I'm doing a random read in a file, and this ran for about 3 minutes. On the x-axis, you see again the buckets on the y of log base 2, and we normalize the z-axis to the percentage of reads. And what you can see here, we also colored things so that it's a little easier to see it because it's a 3D image. What you can see is this. In the beginning, we get very high latencies in the starting. Why? Because every request to read data is a cache miss. You have to get to the slow storage device and retrieve it. So it's slow operations. You see it in the bottom as a histogram, as a bucket to the right. Okay? But what happened near the end of this benchmark, when almost everything is cached? Now you get really good hits. Your performance is really, really high, much, much, much faster. And you can see this bucket moved all the way to the left. But what happens in the middle? This is what you get in the middle, a bimodal distribution. Some operations are very slow because you have to do I/O. Some operations are very fast because you got a cache hit. So you see this bimodal distribution. The interesting part here is there's 1,000-time difference between the fast and the slow operations. That means that just a couple more slow operations could completely skew your average. There's a good question here. Is it okay to calculate averages? Statisticians will tell you, yeah, you can calculate average on everything, but is it meaningful to talk about standard deviations in something that's not a normal distribution? Those are good questions you have to kind of think to yourself. So the dirty little secret here is this. Depending on how long you run your experiment, you're going to get terrible results, great results, or highly unstable results. So what is the answer? Should you do one or the other? The answer that we argued in this paper in Erez is do all of it. Show me the progression of my benchmark over time so that I can convey this information to others to know what to expect at different points in time. Here's another example. Different file systems. This also applies to different storage systems because the code is different, the behavior is different. What we have here essentially is 3 different file systems, and we're benchmarking the throughput over time. And what we see in the beginning is, everyone has terrible throughput. They're all about the same. A little later, we can see that all of a sudden, 2 of the file systems are much faster than ext2, 6 or 8 times better. But as you wait a little longer, that difference kind of slows down, and they're only 2 times faster than ext2. And at the end, there's negligible difference. They're all the same, essentially. So what's going on here? Well, in the beginning, we're I/O bound, so it doesn't matter really what you use. Everything is I/O bound. You really are measuring the performance of your I/O devices, not of your software. And at the end, you're CPU bound or memory bound. So again, you're not really measuring the performance of your system. You're measuring how good is your memory or CPU. The interesting part is what happens here in the middle. There's a 10-minute region where the difference between the highest, the fastest, and the slowest is 10 times. So depending on where you're going to be in that region, you're going to get much better performance results, much worse performance results. It kind of all depends. So that's kind of the dirty secret here, is that depending on how long you run your experiment and what kind of storage system you're layering your software on top, you're going to get very different results. This is not just for researchers. This is also for industry. Imagine that these 3 file systems represent 3 different products that your customer is trying, your product versus 2 other products, and they're trying to compare the behavior. Well, depending on how long they run the experiment, they might think that your product is terrible or wonderful, or maybe doesn't make any difference, and so they'll go with the one that's the cheapest one. All right. Moving on. All right, let me begin to conclude. All right, I said data is everywhere. And storage research, really, I see it as intradisciplinary, not interdisciplinary. They always talk about, you should do interdisciplinary research. And I say, before you do interdisciplinary, you should do intradisciplinary. Go to your colleagues in the next office and figure out what they're doing. And then that will result in a lot of fruitful research. So I'll tell you an example. My first week on the job, 2001, I just finished my PhD. I was writing a lot of kernel code. It was pulling hair to get it all stable and running, difficult kind of coding. So I looked at who are my colleagues, and I found out, there's this colleague who does formal methods and runtime verification. That sounds like a cool thing. So I walk to his office and knock and say, "Hi, Scott, my name is Erez," introduce myself, say, "I hear you're in this field of formal methods, runtime verification. I have this 5 million lines of code in the Linux kernel. Could you just point me to the tool I can use to verify the code, please?" And of course, I was very naive because, verifying that much code even today is very challenging. Scott, being the gentleman, sat me down and said, "All right, let's talk about what you're interested in." And this was the beginning of a 25-year-long collaboration that led to multiple papers, multiple students, multiple grants, papers including in systems conferences like in this one, but also in formal methods and runtime verification conferences. So this is kind of an interesting field that you should think about and go into. Cryptography and security, I always say I wish to see more of this in FAST and in systems conferences. Currently, I'm working on a project. We're looking at long-term archival storage. Very challenging because the problem we're trying to solve is how do you secure data for hundreds of years where we don't really know what the state of cryptography or systems are going to be even 10 years from now. And this is challenging. It forces me to up my game. It forces me outside of my comfort zone because now I have to learn really advanced crypto techniques that I thought I knew some, but apparently there's more advanced things. It's interesting, it's challenging, sometimes a little terrifying, if you will, but it's what makes things for interesting and more exciting work. NLP. I started to work with some people in the NLP field because I was interested in taking all these well-crafted RFCs of various protocols like storage protocols and seeing is there a way that we can analyze them and see if they're correct, if they're consistent, if there's any issues. Can you use NLP techniques to translate those into models that can be verified and maybe even generate prototype code. We only scratched the surface in that project and found all kind of interesting things. We started this project before LLMs were a thing, and then LLM became a thing, and then we converted to using LLMs. But this is a very interesting area that I think more people should go into. Again, data is everywhere, and so storage can really be applied on many different topics. Visual analytics. I collaborated with people in visual analytics because all the fancy graphs that I've shown you, they can only show several dimensions at once. But what do you do when you've collected data that has dozens of dimensions and millions of data points? You need completely different techniques, and the visual analytics field has done this. They've figured out very advanced techniques how to process data and analyze it and visualize it together with some interactivity. So I'm happy to have collaborated with people like that. Again, it led to a lot of collaborations and papers. In fact, the dirty secret is if you're a professor and you want to maximize how much money and grants and papers you have, go and collaborate with as many people as possible because it's easier to get those intradisciplinary grants. More data. We need more data. Data is critical. And we often want to analyze data or to process data or to build a system based on some data. There's a lack of enough data, although I will say that I've seen more and more data sets being released over the last 5, 10 years. 20 years ago, it was very hard to get anything. And it's a lot of it thanks to SNIA for collecting this data set. So Phil was mentioning that we were doing dedupe research together. When I started to do dedupe research, I wanted data sets to build kind of a better dedupe system. And we found out that it was very hard to get any kind of significant data sets that you can analyze for deduplication. And so after some time, we said, why don't we just do it ourselves? And so we spent over 6 years collecting data in our own lab and then curated it and cleaned it up and released it. It's been released for several years, over 5 terabytes of this dedupe data that is well larger than anything else that exists. And now it became kind of the de facto data sets for anyone who wants to do kind of dedupe data sets. It's been mentioned or cited over 250 times, the data set itself. Subsets of it have been downloaded tens of thousands of times. Now, the one mistake I made is I should have used Zenodo to create a DOI for that data set, because people do reference that data set, but they don't have something tangible to cite. So I'm losing sort of tens of thousands of potential citations, but it's a good service for everyone. All right. Next, let's talk about the elephant in the room. AI. So AI is going to obsolete all our jobs, as nobody's going to need anything anymore, right? You can see drops in enrollments, people are moving away from computer science. Is it really? Well, my opinion is this. AI is hungry for data. The more data, the better. And you cannot fit all that data inside those super expensive GPUs. You fit what you can. And when you can't fit there, you have to move and store some of it in the system RAM. And when it doesn't fit there, you have to move it to non-volatile storage devices. Now you got yourself a storage problem. In fact, a multi-tier storage problem. So scaling AI systems is really a storage problem. We should all consider it as such and start to work on it. All right, I'm going to do something bold now, all right? I have come up with a way to characterize what is going on. Something that I felt in my heart for many years, but couldn't kind of articulate it until I was sitting down and actually preparing this talk. And I came up with the following axiom. Computer systems, when scaled, become a storage problem. Right? You take any computer system, the data is paramount. The data is more important than the hardware, than the software. Even people come and go. So the data is really the intellectual property of every company. It's the most important thing you can have. And so when you scale that system, the data becomes too big to fit in any one particular point. So now the data has to be diffused in many different places and different kind of storage or memory devices, and it becomes a storage problem. And that's why I said in the beginning, life is good, because I think there's a lot of potential for us to do storage research for the foreseeable future, because I don't see less data. If anything, more and more data is being generated and used any time. So let's see if this survives the test of time. Next, I have a shameless plug for journals. I can't stand up here as editor-in-chief and not say something about it. When I took over as editor-in-chief, I was pleasantly surprised to find that 2 of my papers were in the top 10 most downloaded papers that ACM TOS has had. And it turned out one of them is a 2008 study of file system benchmarking, and the other one is a characterization of fuse performance and optimization. And these were survey papers, and so they became kind of the de facto standard for anybody who's interested in one of these topics. They go to those papers. There's no upper page limit. You can use it to expand papers like here and fast. There's always more room for more data, more analysis, more information. Journals are excellent for survey papers. We have done a special issue in last year, 2 parts, one released last February and one in August, called Past, Present, and Future of Storage Systems. And we had 11 papers, each one taking one topic and creating the authoritative paper on that topic, from DNA to silica to holograph, and yes, even tape. I was so happy to see a paper on tape technologies yesterday. And the dirty little secret is this: if you create an authoritative paper on one particular topic, everybody will cite your paper and none of the ones that came before it. So that's how you siphon citations from others, all right? So there's a lot of things you can think about. How about somebody write a paper on CXL, everything there is to know about CXL, or KV caches in LLMs, or AI for storage, storage for AI. There's a lot of these kind of topics that you can create the paper that people will keep cite year after year after year. Okay. I ask you, please, if you're going to be citing papers, also look for any journal versions of them and cite both the conference and the journal paper, because usually the journal paper is a superset, has more information in it. So, before I end, I want to tell you another story. 1988, I took my first OS course as an undergrad. I implemented symbolic links in the Minix operating system. I was on top of the world. It was so challenging, so exciting. It worked. It made me feel like, you feel powerful, like I control things in the bottom. I have a lot of power inside the operating system. And so with the first opportunity, I jumped on an OS course, OS project. And the project was to take a device driver for a robotic arm of another researcher and port it from an old BSD to a new BSD version. After a week of struggling with it, I realized I'm way over my head. This was way too complicated. I didn't realize how complicated it is, but it was exciting because I really wanted to solve this problem. So I went and asked for help. This research scientist named Chris, I asked him, hey, can you help me take a look? And we sat down, and for 2 to 3 weeks, we're struggling with the code, try to port it. Eventually, finally, we get it to work. We see the robotic arm moving. It's not smacking anyone in the head. Good. And so we're so satisfied. We kind of slouch back in our chairs and kind of like look at each other, grinning. Yes, we got it. It's working. And then Chris, who has more experience at the time in kernel development, tells me the following. Kernel hacking is hard. Really hard. But once it works, man, it's better than sex. And with that, I'll take your questions.